Okay, so yeah, I will start. I think it will be a short presentation since I'm trying to improvise. But it is it is an easy to read paper actually, and it's really interesting, right? So this paper talks about preventing tiny performance regressions at hyperscale through pre-production testing. Like what they actually trying to do is just detect the performance regressions, right? So the ServiceLab is the system for detecting the performance regressions in production systems at Meta, right? So like really large scale, Facebook and like a bunch of other apps at Meta, yeah, I guess to give some example of the scale, one of the services that they talk a lot in terms of like testing is front FAS, right? And that is a front end function as a service platform at Meta. And they give some like really impressive numbers. Actually, I think the numbers are here. More than 10,000 engineers write code on this platform. And they have thousands of code changes committed daily. And when they talk about testing front FAS, they're not only testing the actual like platform, they're testing all of these applications that that exist on the platform, right? So there are like a lot of changes. It's a highly dynamic environment with a lot of engineers, making their changes, contributing their changes. So, if something is, slowing down the service or slowing down the application running on the service, that can have like a considerable impact, right, at the scale of Facebook, at the scale of Meta. And on top of that, there's like the amount of changes, right? Even if, each change has such a tiny, tiny, tiny impact over, over some time, those tiny little regressions, they can end up into some like really, really serious problem, right? So these are kind of the main problem that they want to address: how to detect regressions that are like super tiny, right? So as tiny as 0.01% performance regression, right? So I mean, like this is like so small that you can consider it noise. Yeah, so what is a regression, right? As it was answered in chat, so when they talk about performance regressions is, let's say you make a change as an engineer, right, to an application, and that change causes the application to run slower, right? So that performance degradation is what they refer to as the regression, right? So if your change made the system, made the application 0.01% smaller, so 1/100% smaller, that's what they want to detect, right? So, like very, very small changes in performance of your applications. And, while they want to detect this, there are some challenges. One of the bigger challenges that, this system faces is essentially running the tests on a heterogeneous environment, right? So Facebook, or like all of the applications within the Meta, they run in a private cloud, right? So they have their own data centers and whatnot, but they manage those data centers as a cloud. So these data centers are large, right? These data centers evolve, and that means that these data centers have all kinds of different hardware, right? So you may have different generations of CPUs, different generations of memory, solid state disks, you name it, right? So how do you essentially perform this testing at scale on the hardware that is not necessarily the same, like across the board, right? So yeah, and the other goal is like supports in other like services, right? So they want to be able to take this ServiceLab and use it not only with that front FAS, but with other services at Meta. So I'm gonna go and create a blank page so I can start, so I can draw some stuff. Because the paper, while it's written in a like very like nice and easy to parse language, it doesn't have a lot of graphics. So the paper presents this system called ServiceLab. Yeah. And what this system does is essentially A/B testing. What is A/B testing, right? So that's a type of testing where you compare something against the baseline, right? And you kind of run the same thing. Like maybe in the context of UX, that is more well known. So like A/B testing would be like when you run two versions of the same software and you present one version to one user, another version to another user, and then you measure something, right? And how those two versions compare. So in the case of ServiceLab, when they mean A/B testing, they mean that they actually test production software, I will abbreviate it with PS, against the system under test. So the software version that they need to test in like for regressions, right? So system under test, they call it SUT or SUT. Like how do they actually perform this test, right? So obviously it needs to run like this is a pre-production test, right? So they cannot put system under test into the production. They cannot like force the real traffic into the system. So they, the ServiceLab is this like sandbox, and this sandbox literally takes one machine. Um, and it puts the production software on it, and it takes another machine, and it puts the system under test on it, and they run the same workload in both, right? So they run this workload, and they use the statistical analysis. They run like a bunch of statistical tests to try to figure out if there is a difference in system under test compared to the production system, right? So there is like a big flaw in this like general approach, and that is they actually run in the cloud, and as I said, like they have heterogeneous like types of hardware and software and whatnot. So a good chunk of the paper, a big problem for them is like, how do we ensure that the machine one that they get and the machine two that they get are comparable enough? Like, how do you make sure that they're like almost the same? Right. And they claim that it's difficult. Like they cannot always get like identical machines. One of the reasons they say is, well, they run it like a private cloud, right? And they have like around 10 or so different machine types or server types. But those are too broad like categories, and each server type may actually still have variations, like different CPU generations and whatnot, right? So even if they get like two machines with the same server type, they're not guaranteed to be the same. If they get two machines and they put like different versions of image in it, like different kernels, they also experienced they like did the evaluations. Different kernels experience different like noise and different variations. So they want to minimize all of these factors, right? So yeah, so the big deal is for them to find, the machine 1 and machine 2 that are, as identical as possible, right? They call it machine 1 and machine 2. It's like they don't get partial service, they don't get virtual machines, they get the full machine. And that is to make sure that there is like no noisy neighbor syndrome and like other workloads that may run on the same like physical machine, like they don't exist essentially, right? So everything is done like for the sake of reducing the interference, right? So you find machine 1, find machine 2, and you run that production software PS and the system under test in parallel, and you feed them with the same workload, right? So you feed them with some kind of workload, and this workload is actually production, right? So they, for the most part, they don't use artificial workloads. They don't use micro like benchmarks and whatnot. They use real production workloads that they just remembered. So like clients issue RPC, for example, against this front FAS, right? They remember those RPCs somewhere so that they can replay them and reissue, right? And that's how they ensure that they have a realistic workload, because it is a real workload. It is like a real workload, and they just replay it. Yeah, so another important consideration is the software test, whatever that piece of software doesn't live in isolation. Right, so that means that typically we also have a bunch of dependencies. And at Facebook, at Meta, they claim that it's unrealistic to like often copy those dependencies and make like a tested version of those dependencies, because again, like the scale of those dependencies matter, right? So if you're talking about this like front end application that will most likely will interact with, let's say, tower system, which is like the graph, right? You kind of need the scale of this system to arbitrary copies of it. So, test environment and the system under test, they do interact with real production dependencies for their, like for whatever they need, with a few exceptions, right? So all of these interactions are read only, right? And if any of this need to write, then like you're not allowed to do that. So you will need to provide some kind of mock service or mock database if you need to have, if you're trying to write. Another reason why they want to include the real dependencies is to actually check if the versions, like the different versions, the system under test, not only like itself, the dependencies to use more recent, but they can look at like how often all of these dependencies are used and whatnot. So yeah, that's kind of the system in a nutshell. And the paper has like a lot more details, not a lot of pictures. They talk about like a bunch of other systems that they take that they test: ML prediction, ranker, data aggregation, and So yeah, I want to kind of circle back slightly to heterogeneous systems, right? So they claim that they have some like types, different CPUs. Also claim that they have to test in parallel as opposed to just get one machine and test back to back, because like testing back to back is just going to take like significantly more time, right? So for the sake of being able to run those tests relatively quickly, they need to test them in parallel. So they need to find close enough machines. Yeah. So and yeah, like all of this testing is like their like server level software, right? So we're not talking about like testing the apps. This is just like their data center level software. There are a few other interesting things that kind of tidbits of information on heterogeneity. Some CPUs have a lot more variance, a lot more variance than other CPUs. Right, so they try to stay away from the CPUs that themselves are kind of noisy. So they will try to get the machines with the like CPU types that are less noisy. Right. Also interesting part. This CPU is like 8 years old, so I'm kind of surprised it's there. I guess it should be like getting close to the end of its like lifetime. The same with like kernel versions, right? So some versions of Linux kernel in their testing show a lot more variance than other versions, right? So they stick with like whatever the combination of hardware and software that gives them the most predictable performance. For the statistical methods, they have like an entire section on this, and it ranges from like a plain like student t-test to like a more sophisticated method. And the system itself decides on the statistical like method to use. And the way it does it is it actually tries to figure out like it also does things they call AA test when they compare the same version of software. So let's say you put the production system against the production system and see if you like observe the difference, right? So it's the same software, so there should not be a difference aside from like all of this like random fluctuations or because of heterogeneity and whatnot. And they can use this data to fine tune like their experiments and fine-tune what statistical like methods they will actually use to decide whether there is a regression or not. And those like decisions on what statistical methods to use, they actually change over time. So it's not like they decided once that for a particular system they're going to use just that, right? It will change over time. And yeah. I think this is kind of the big picture of the system. I do want to point. I want to go into some evaluation. I'm not gonna like show a bunch of pictures and whatnot. What was kind of interesting for me was the false positive rate, right? So in their like experience, right, in their testing of their system, in their experience of using it, 57% of the regressions that the system identifies are true positives. The 15% are false positives, and what they say 28% are unknown, right? So that's when the engineers, when they get this report, they're not sure if it's true or not. So from this data, they claim like if they take this 28% and they use the same distribution of true positive to false positives, they claim that they have around 21% false positive rate, right? So, that sounds actually quite high, but they still like claim that this is like a major success. And like 21%, out of like all of the regressions that they signaled, and only 0.3% of changes actually get signaled for regression, right? So what they calculate is that for like I like this one. Assuming a developer writes one diff per day, they will experience a false positive about every like 20 years. So they claim it's a success enough for like them to use this tool and for the engineers like to like not discard when they see like a positive like regression to actually like do the proper investigation and confirm whether it is or not, right? So the tool is not perfect. It still requires an engineer like to confirm the the regression, but they claim that like the smaller false positive rate is going to be the more likely the engineers actually to take it serious, right? Obviously, if everything is false positive, then the tool is not useless and engineers aren't going to use it. So yeah, I think I'm gonna stop with my kind of semi-improvised presentation, and maybe we can go to questions.